summary of some stuff that we got last time and maybe a discussion of how to approach that homework problem. So let's start with this. Let's fill in a table that we got last time. If I give you absolutely any angle theta, and I ask you for the cosine of negative theta, what does that simplify to? Just cosine of theta. And I guess there are two ways to check that. On the one hand, like, we literally have a page in the notes that you can just look at. It's the cover page from the previous section. Well, the section that we'll be finishing today. On the other hand, that corresponds to rotating down by the same angle, theta. Yeah, those have the same x coordinates, so they have the same cosine. Sine of negative theta. Yeah, but say it louder. Negative sine theta. Same thing. Y value became negative. Pi minus theta. What is the cosine of pi minus theta? I hear a negative cosine. People agree? Excellent. And one way to see that is, well, there's an angle of pi, so go to pi and then go back by theta. My unit circle is absolutely terrible, but that's because I'm basically standing in a trash can when I write that. X coordinate became negative, cosine's negative. How do the sine of this point and that point compare? They're the same. So what's the sine of pi minus theta? Same as the sine of theta. Pi plus theta. What is the cosine of pi plus theta? Well, I guess we'll play the same game. Say louder. I hear a negative cosine. People agree? All right. How about sine of pi plus theta? Negative sine theta. And again, why is that true? It's because there's an angle of pi. Now rotate forward by theta. That's reflection across the origin. X and y became negative. Pi over 2 minus, and this is the one that maybe we didn't try the picture for to get in class, but we stated it at the beginning by looking at like a graph of sine and cosine. What's the cosine of pi over 2 minus theta? Not quite. At least if I heard you correctly. It will turn out to be sine of theta. Is that what you said? Okay, okay. And we'll talk about why that one's true in a moment. Maybe I'll draw on this picture why it's true, and then give another reason in the notes. Sine of pi over 2 minus theta becomes cosine theta. Sine of pi over 2 plus theta. Why do these switch? It should be cosine. Cosine of pi over 2 plus theta is negative sine theta. Sine of pi over 2 plus theta is cosine theta. And maybe I'll draw a picture for those last two. How big an angle is pi over 2? It's like a 90-degree angle. It's a right angle. So if I want this angle, then I want to go forward by a right angle, and then back by theta. So maybe just for emphasis, I'll shade in that little sector of the circle to remember that word from a while ago. And this one. Do those two sectors look like they're related somehow? By how? Reflection over, not the origin, but like, I think you're, make that hand gesture. Yeah, yeah. Reflection over the line y equals x. Reflection over that line. Oh, notice, that swaps x and y coordinates. Cosine of pi over 2 minus theta is this x coordinate, is the same as the y coordinate. So cosine of pi over 2 minus theta should be sine of theta. Sine is the y-coordinate here, is the same as the x-coordinate of the original. Sine of pi over 2 minus theta is cosine theta. And if you wanted now pi over 2 plus theta, well, there's pi over 2 plus theta. The picture is getting unreadable as we progress. But that's okay. It was only meant to be used to get a single thing at a time. Well, that little wedge looks like the same as that little wedge, except x has become negative. So these should be the exact same as those, but the one with cosine should become negative. How does that feel as far as reasoning goes? So on the one hand, like, you have that table. You can, like, put that table on, like, your note sheet for whatever midterm. I think there's one, like, at the end of next week or something. It might be Monday of the week after. It's not, it's close-ish. So you can put all these formulas on that sheet, but do you think you could just, like, draw a unit circle and reinvent them on the spot if you had to? Yeah. And let's use them to do something. Let's do something that'll look an awful lot like the open-ended homework assignment from yesterday. So let's suppose I give you an angle. I tell you its sine is 0.1, so a tenth, and that this angle lives in quadrant 2. Let's try to compute a bunch of these. How many people have looked at the homework assignment yesterday already? They look an awful lot like this? Yeah, it's a different number. The number in fact is rigged to make it easier than this computation, and it's in a different quadrant. Otherwise, same question. It's also like the thing at the back of this section of the notes. All right, let's try to do it. So let's start at the top and go down. If you know sine is 0.1, how do you find cosine? What's like the most important identity about trig functions? What's the relationship between sine and cosine? Yeah, something equals 1 about them. What do you mean by they?
It has to be cosine squared plus sine squared.
Yeah. Add up the square of sine and the square of cosine, you always get 1. I want to know cosine, well, I guess alpha is what I want, not theta. I know sine is 0.1 squared. I would like to know cosine. I'll call it just c so I don't have to keep writing cosine of alpha. Time for something we can solve for c? Yeah. Let's do that. What seems like a good first step if you want to solve this for c? Square root of the 0.1. Did I square that correctly? Excellent. What next? Subtract it to the other side. Did I subtract correctly? Should there be another? I think you lied to me when you told me that I squared it correctly. 1/10 squared is 1/100th. All right, and then subtract it. Okay, cool. What next? Oh, cool. So C1 is the cosine of alpha. And that's the square root of 0.99. I screw anything up yet? In this case, I did. I intentionally did something wrong this time.
Plus or minus.
And I think it matters this time. Because this angle is set to be in quadrant 2. So plus or minus? Minus. We could like turn 0.99 into a fraction and pull out some like perfect square pieces, but I think maybe I'm in a decimal approximation kind of mood. What is the square root of 0.99 about? 0.995. Okay. Cool. So, oh, and it's negative. I lost the negative sign that I just harped on so hard. Is this enough information to now start going down the rest of them, automatically, more or less? What's the cosine of pi over 2 minus alpha? Well, which one of the rows of this column look useful? Here I see pi over 2 minus an angle. Over there, do I see pi over 2 minus an angle in one of the entries? Here. So apparently this is equal to sine of that angle. It's not called theta over here, it's called alpha over here. Do you know what sine of alpha is? What's sine of alpha? And I guess, let's do one more. Yeah, over that one. Sine of pi over 2 minus alpha. It'll become cosine of alpha. Do you already know what cosine of alpha is? Yeah, it's like that. Cool. That seems sensible? Nice. So now I'm going to turn the projector back on. And maybe I'll point to a bit of homework. Does that look like you have enough now to do maybe all of this homework except for these 4? Nice. Those 4 are supposed to be heard, and we'll get the tools to do them right now. Right now-ish. First, let's finish up the argument we were working on for trig functions of pi over 2 minus theta. So we talked about them kind of informally back there by thinking about reflection over the line y equals x. You can also do this by thinking about triangles. If you draw a right triangle with one angle equal to theta, then the other angle will be pi over 2 minus theta. So that top right angle is pi over 2 minus theta. And now let's use SOHCAHTOA stuff to compute everything else. By looking at this triangle, what's the cosine of theta? What's adjacent to theta? What's opposite? Well, yeah, so that's everything, right? X over the hypotenuse. What about sine of theta? What's opposite theta? Y. So it'll be opposite over hypotenuse. But we can also now think about pi over 2 minus theta. So let's compute cosine of pi over 2 minus theta using these rules. What's the side adjacent to pi over 2 minus theta? It's y. So cosine of pi over 2 theta will be adjacent y over hypotenuse. Oh, neat. Is that just equal to one of the 2 things in the previous line? Yeah, sine, I guess. Cosine of pi over 2 minus theta is equal to sine of theta. Let's also think about sine. If you want to compute sine of pi over 2 minus theta using SOHCAHTOA, I need opposite over hypotenuse. What's the side length opposite? Well, There's the angle pi over 2 minus theta. There's the opposite side length. It is x. Oh, neat. Is that like just the same as something in the previous line? Awesome. Sine of pi over 2 minus theta is equal to cosine of theta. I think we could now compute secant, cosecant, and cotangent using all of these same tricks. And like, you kind of know what to do. So secant is 1 over cosine, and cosine became sine. So what do you think secant of pi over 2 minus theta will become? Maybe we should write it out? Let's write it out. So let's try to compute secant of pi over 2 minus theta. Secant is 1 over cosine. And I still have this same angle. So that's just what secant is. What can I replace that cosine of pi over 2 minus theta by? Sine theta. So this is the same as 1 over sine theta. Oh, what is 1 over sine theta? Yeah, cosecant. So secant becomes cosecant theta under this transformation. And hopefully that's not terribly surprising. Secant is like the thing that's the reciprocal of cosine. Cosine became sine, so cosecant should become the reciprocal of sine. What do you think should go in the like next blank oval? Probably secant. And maybe instead of walking it out, let's just kind of imagine what would happen here. So if instead I wrote cosecant there, right there I would see sine in the denominator. Sine of pi over 2 minus theta would become cosine theta. 1 over cosine theta, yeah, is secant. How about tangent and cotangent? Think we can do those? Yeah, let's try to do it. And I think, like, I'll talk about one or the other, and those who want to walk independently should do the one that I don't do. Should I do tangent or cotangent? Tangent? Cotangent. All right, I think the vote was 1-0 with a high turnout. Let's try to walk on tangent. So let's try to compute tangent of pi over 2 minus theta. What's tangent in terms of sine and cosine? Sine divided by cosine. This will be sine pi over 2 minus theta divided by cosine of pi over 2 minus theta. Now let's look in the numerator. In the numerator, I see sine of pi over 2 minus theta. What is that? Cosine theta. What do I really see in the denominator of this? Sine of theta. So the sine became cosine, the cosine became sine. Oh, cool. What's another word for cosine theta divided by sine theta? Cotangent. So if tangent became cotangent, what do you think cotangent will become? Tangent. And right, there's no weirdness with negative signs showing up. All right. So the last one I want to get, we'll develop some of these like skills you'll need to do those 4 things in the homework that we didn't talk about in detail. Let's try to figure out trig functions at pi over 2 plus theta. And I won't try to do any geometry to do this, although I guess like there is some geometry you could do. Instead, I'll just try to use facts that I already know. So I know how to do pi over 2 minus an angle. Well, addition basically is subtraction. Instead of adding, I could subtract a negative. Oh, cool. Let's just do that. To compute cosine of pi over 2 minus theta, let's compute cosine of pi over 2 minus theta. And in order to like emphasize the thing that I'm hiding right now, let's just put this in a box. So instead, tell me what is the cosine of pi over 2 minus box. Do I have a rule that says what cosine of pi over 2 minus an angle is already? What's the cosine of pi over 2 minus a thing? Sine of that thing. Cosine of pi over 2 minus box is the same thing as the sine of box. But of course, box isn't the variable I want. What do I want to put in that box? Negative theta. Cosine of pi over 2 minus theta is the same as the sine of minus theta. All right, whenever you see like multiple different complicated algebraic steps that you want to do one at a time, sometimes it's nice to go and like forget all the complicated algebra you don't want to do right now. Do the algebra you do want to do right now, and then put back in the algebra that you skipped. Okay, so I see the sine of negative theta. What's the sine of negative theta? Possibly by looking at an appropriate row on the board. Negative sine theta. Oh, so what's the cosine of pi over 2 plus theta equal to? Negative sine theta. Hopefully that agrees with what's on the board. Awesome. So that's where this negative came from. It came from this negative sign. Could we do the same thing to compute the sine of pi over 2 plus theta? Let's try to follow the same tricks. So I'll think of this as sine of pi over 2 minus theta. But I won't worry about that minus theta right now. I'll put it in a box, and I'll forget about it for now, and I'll remember it later. So instead, I'll think about sine of pi over 2 minus box. Do I have a rule that does sine of pi over 2 minus box for me? Yeah, sine of pi over 2 minus box is equal to cosine of box. And what's the thing I want to put in that box? It's whatever was in the box before. Cool. So now I have myself in this situation where I just need cosine of negative theta. What's the cosine of negative theta? Negative sign doesn't matter. That is just the cosine of theta. Groovy. So in order to complete the lines in the homework that we didn't already talk through, think about that idea. If you want to think about 3 pi over 2 minus an angle, is 3 pi over 2 like a sum of some things that you do understand? Yeah, it's like pi and then an extra pi over 2. So instead do cosine of pi plus pi over 2 minus alpha. There's a thing you can put in the box. Do you know what cosine of pi plus does to trig functions? Yeah, it's on the board anyway. So use that. And I'm not going to like do that because that is homework, but think in terms of that to complete those items. Cool. People feel pretty good? Nice. So, I would like to get a start right now on a new idea. We have some familiarity with the trig functions. Let's start undoing trig functions. All right, like that fits into the pattern that we've developed for a lot of other things, right? Since exponentials are things that we care about, we invented logarithms to undo them. If, like, squaring is something you care about, you have to invent something to undo squaring, like square roots. Same thing with trig functions. If you want to solve an equation that involves a trig function, you need to be able to undo that trig function. So, let's start in on that. Inverse trig functions. So here's the motivation for inverse trig functions. Let's suppose someone asks you, solve the equation sine of x equals 1 over 8. We definitely don't have the tools to do that right now. I guess there are some things we can do. Could you like graph sine of x? And also just like see when the y value is equal to 1/8? Yeah. In fact, picture the graph of sine of x. How many times is sine of x equal to 1/8? Say that louder. Yeah, in infinity times, as many times as you want, right? Because it keeps on wiggling up and down. So there's something complicated there. So here's the tool that we'll make up. So let's think in terms of triangles. So let's suppose I give you a triangle, a right triangle, opposite side length 1, hypotenuse length 8. And I ask you, what is that angle? Is there a single angle that, like, only one angle satisfies that triangle? Yeah. So there's, like, only one value. It's an angle, well, it's an right triangle, so it's going to be an angle in quadrant 1 if you were to draw it in a unit circle. It has sine equal to 1/8. Just like how we did with log, right, like log base 2 of 5 is like the number that is the power you need to raise 2 to get 5. Same thing with these. This angle with sine equal to 1/8 that's in quadrant 1, we will just call sine inverse of 1/8. That is the inverse sine of 1/8. We'll give it a name. That also lets you like ask a computer to compute it. It might also be called arc sine of 1 over 8. Or depending on exactly what your calculator expects, a sine of 1 over 8. And here's like the thing at a glance that makes this powerful. Once you have that thing, if you have a calculator that can compute it, you can compute it using a machine. So go ahead and take out your machines, if you have one, and tell me, what is the inverse sine of 1/8 about? What'd you get? If you have a button that does it, that's easy to find. You definitely do, yeah. About 7.18. Does anyone get an answer that disagrees? I mean, I want like there to be a 50-50 split because there are two different answers that you'll get.
I got
0.125. What explains the two different answers? Radians versus degrees. That's the degree measure of this angle. Here's the radian measure. So, as always, just make sure you know whether you're in radians or degrees. And, I don't know, in this particular prompt, was it clear whether I cared about being in radians or degrees? No, so just make sure to effectively communicate what mode you're in. So here's an informal definition. Inverse sine of 8 means the, and I'll put this in quotes, simplest angle with sine equal to 1 over 8. That's all inverse sine means. It wants to capture the simplest angle whose sine is 1/8. Same thing with inverse cosine. And I've put this negative there for a reason, because you can see negatives showing up, so I want to have them show up oddly. Inverse cosine of -8 means, and again I'll put in quotes, the simplest angle with cosine theta equal to -1 over 8. That's all the inverse trig functions mean. If someone asks you for the inverse sine of 0.1, they're just asking you what is the simplest angle whose sine is 0.1. And sometimes you can compute them by hand, sometimes you can't. When you can't, you resort to a machine. What the machine's going to do is it's going to do the thing that I've said the machine does like every time. It's going to compute some Taylor series, which is something that you'll learn about in Calc 2. All right, so let's see a concern you might have about this.
So, there's the graph of sine of x. That's like a y value that's around 1/8.
How many times does that horizontal line cross the graph of sine of x? Infinity times? I mean, 4 times in this graph, but if it kept on going, you would see infinitely many times it crosses. Does that function pass the horizontal line test? Nope. So does that even have an inverse function? Nope. So it's kind of weird that I want to find an inverse function, right?
And I guess the same question for cosine.
Is cosine 1 to 1? No, it's also like infinity to 1.
So do these have inverse functions? No.
I want to study inverses to these functions anyway, so that's going to be a problem. But it's a problem that you already know how to solve, because you have solved this problem before. Picture the y equals x squared function in your head. Is that function 1 to 1? But if I ask you, like, what undoes squaring, what do you tell me? Square roots undo squaring. So even though it's not honestly 1 to 1, you can still cook up a fake inverse. And let's kind of remember how.
So like, there's y equals x squared. It's not 1 to 1.
So instead, let's only pick up some of the graph of y equals x squared. And let's pick up as much of it as we can while still having it be 1 to 1.
So I guess here's how to do that. So in black, here I see y equals x squared with x bigger than or equal to 0.
Is that black thing that I just drew 1 to 1? So that black thing that I just drew, does that have an inverse function? Sure does. The square root is the inverse of that black function. Do you think we could do the same thing with sine and cosine? Let's record as much of sine as we can while still being 1 to 1, and record as much of cosine as we can while still being 1 to 1. We'll only use that itty-bitty piece of the graph and get an inverse function using that. So, doing that,
Let's start with sine. Let's see. I'll start at 0 because, like,
0 is like an important number. How far to the right can you go on the graph of sine before it stops being 1 to 1? At that peak.
so if I go up to here, it'll turn around and stop being 1 to 1. How far to the left could I go while still being 1 to 1? That, like, anti-peak at the bottom? I don't know, maybe valley, trough? Well, turning point. Turning point is the right word. Or possibly local maximum.
If you only saw
This piece of the graph, would you say that that sucker is 1 to 1? So could you invert that graph? Nice. Maybe just for the sake of completeness, you told me was you go from like that valley to that peak. What are the x coordinates of that valley and peak? So that one's definitely negative, but it's negative what? Possibly look at like, I don't know, let's look at the unit circle. So that's like, Starting at 0, you rotate down until you get to the most negative y value, -1. What angle is that? Negative pi over 2? Or 90 degrees if you want to walk in degrees, but I'm walking in radians. And that goes up to pi over 2. So I'll restrict the domain of cosine to just be that. Same thing, nope, domain of sine to just be that. Now let's talk about cosine. So again, I'll start at 0, and I'll go forward as far as I can while still being 1 to 1. How far can you go while still having cosine be 1 to 1? Guess it's to that value, right? What's the x-coordinate that corresponds to that value? I think it's pi. Right, cosine of pi is -1. So, if you only see that much of cosine, does that look 1 to 1? So here's the trick. We'll restrict the domain. Now, these things are 1 to 1. Gesundheit. And that'll show up on the next page. So on the next page, here we have restricted the domain of sine and cosine Gesundheit and only drawn that much of the graph. Do those graphs look about like what we got on the previous page by shading in red? Okay, that's good. Gesundheit. I don't know, do you think that that shading is the only shading I could have done to get these things to be 1 to 1? No, you could have done any. The conventional thing is to do what I just did, because that's like, I don't know, you like to include 0 and then you want to go forward. So it's like the most natural choice, but it's not the only one. Gesundheit. So, I've restricted the domain accordingly. So let's record the domain. If this is all you see of sine, what's the domain? Negative pi over 2 to pi over 2 inclusive. And you may as well get the range now too. What's the range? -1 to 1, including both. So that's good, because that's the same as the range of like all of the graph of sine. So I at least like still achieve all the output values. Same thing for cosine. What have I restricted the domain to? 0 to pi, and the range is still -1 to 1. Now that we've restricted those domains, are those things 1 to 1? Do those things have inverse functions? Now I'm ready to say exactly what I mean by inverse trigonometry. Inverse sine, also called arc sine, sometimes also called a sine, depending on what the machine you're using expects, is the inverse to the function sine of x after you restrict the domain to be negative pi over 2 to pi over 2. That seems sensible? So here's a way to interpret that. Inverse sine of y is then an angle, maybe I'll call that angle theta, which sits between negative pi over 2 and pi over 2, which has sine of theta equal to y. So inverse sine of y says, you tell me what y value you would like. I will give you an angle. That angle will live between negative pi over 2 and pi over 2, and it will have the desired y value. That's what inverse sine measures. And you know what, let's just check that that actually works. I'm going to pull up Desmos. Give me a thing you would like to plug into inverse sine. 2. That's a That's a choice that, give me a number between -1 and 1. 0.5. Okay, good choice. So, let's think about arcsine of 0.5. This number should have the property that at that input value, sine should be exactly 0.5. At that input value, is sine exactly 0.5? And in fact, is Desmos also telling you what the inverse sine of 0.5 is equal to? Yeah, keep that in mind. Groovy. Same thing for cosine. Inverse cosine, also called arc cosine, is the inverse function to cosine after you restrict its domain to be 0 to pi. Fair enough? So what does that mean? That means I think x is a better thing to say because cosine is like an x coordinate. So I'm going to replace that y with an x. You don't have to if you don't want to. Is an angle. I'll continue to replace that angle with theta, which lives between 0 and pi, which satisfies that cosine of theta is equal to x. So inverse cosine is the operation that says, you tell me what x value you want. I will give you the simplest angle, the angle between 0 and pi, which achieves that x value. That seems sensible? Seem good enough? All right. So, maybe we'll read off the domains and ranges of inverse cosine really quick, and then I'll tell you why I was unhappy with your choice of x equals 2. There was no reason that you could have known I would be unhappy, but how do you get the domain of an inverse function? It's the same as the range of the original. So the domain of inverse sine should be the same as the range of sine. What's the range here? -1, 1. So what's the domain of inverse sine? Do you see now why I was upset with the idea of plugging 2 into inverse sine? And in fact, right, like any calculator will give you like some sort of domain objection. If you ask Desmos for the arcsine of 2, it'll say no. Same thing for inverse cosine. What's the domain of inverse cosine? Let's see, it should be the same as the range of cosine. What's the range of cosine? -1, 1. Excellent. Let's also discuss the ranges. What's the range of inverse sine? Well, the range of inverse sine should be the same as the domain of sine after you restrict the domain. So what's the range of inverse sine? It's that. Range of inverse sine is -pi/2 to pi/2. How about the range of inverse cosine? 0 to pi. Nice. And in fact, I bet we could graph these inverse functions by hand. How do you get the graph of an inverse function? You just like swap all the y's and x's? So if there's the graph of sine, then the graph of inverse sine, I guess, looks something like that. The exact same graph, but y's and x's swapped. There's the graph of cosine. Graph of inverse cosine will look something like that. Nice. And with 6 minutes left, let's talk about how you can actually use the unit circle, use things you already know to compute. So, let's suppose I ask you to compute the inverse sine of 1/2. Let's think about what that means. And, I mean, is that exactly like a thing that I just had Desmos tell me what it is? So do we already know what the answer will be according to that? How many people just have the memory to remember that? I hear pi over 6. Let's see why it's pi over 6. So let's think about what inverse sine means. If you want inverse sine of 1/2, then you want an angle which is in between negative pi over 2 and pi over 2, and which has sine equal to 1/2. So I'm going to do that by pulling up the unit circle. I think I have space under my document camera for both if I move things judiciously. All right, so you want to look in the unit circle. You want to look for an angle between negative pi over 2 and pi over 2 where sine, the y value, is 1/2. Do you see an angle on your unit circle which has a y value of 1/2? What angle do you see? I hear a pi over 6. Do you see another angle? 5 pi over 6. I'm going to list both of them. Sine, inverse sine has to be an honest-to-God function, so it can't be both. Let's talk about why it's pi over 6 and not 5 pi over 6. So pi over 6 and 5 pi over 6 do this. But they both have the right value for sine. Are they both between negative pi over 2 and pi over 2? Nope. 5 pi over 6 is like almost pi. It's way bigger than pi over 2. Is pi over 6 in the right range? Nice. So, there we have inverse sine of 1/2. I think with my 3 minutes I have left, let's do one last computation that will be pretty similar. Let's try to compute, I know it says inverse sine there, but that's totally a typo. Inverse cosine of negative root 3 over 2. And to do that, what do you need to do? You need an angle that's in the range of inverse cosine. And which satisfies that cosine is equal to negative root 3 over 2. So, let's do that. Pull out your unit circle. On your unit circle, do you see an angle where the cosine is negative root 3 over 2? Should I project my unit circle? I'll project my unit circle. So, do you see an angle where cosine is negative root 3 over 2? What angle do you see? I see 5 pi over 6. Do you see another angle that also has that same cosine?
Negative 5 pi over 6.
And maybe I'm even going to list one more, though the correct answer is already on the place, on the paper right now. 7 pi over 6 also does the job. That'll also get you to this place. And right, that's not a surprise. Cosine takes any value it takes infinitely many times. You could write down infinitely many things in the list. Only one of them should be between 0 and pi. Which one of those is between 0 and pi? 5 pi over 6. So this is equal to 5 pi over 6. Cool. So the point there is you can use the unit circle to compute inverse trig functions. All right. So I'm about at time. Here are some relevant announcements. I'm not going to be here on Monday. I've already posted a recorded lecture to check out on Monday. I'm going to add a little bit more to that lecture just to finish up this one. So there will be some stuff for you to watch over the weekend / Monday that will get posted. Some of it's already posted, the rest will get posted tonight. I won't be here on Monday, so I guess I'll see y'all on either Tuesday for my office hour. I might not be here for my Tuesday office hour. I think my flight gets in late enough on Tuesday. So possibly Wednesday then. But keep in mind, if you have any questions you want to ask about, I'll be available via email.